All right, let's go over. So you may or may not have got all 5 answered, but just for time's sake, there are some other problems that I want to get to. So, and I am recording. So now, as long as tech doesn't fail me. So some of the key things, hopefully you caught this. They start from rest. So initial velocity for both is going to be what? 0. Initial kinetic energy will be 0. Angel and Brittany snowboard, we said, down a hill is shown. Angel rides down the steep side, Brittany on the shallow. Now I know it doesn't look it, but if these were ramps, right? So kind of your best ramp here, steepness alludes to the angle, right? So who has the greater angle? Angel. And so this, I'm just going to make up something right here. So maybe it's 2 theta. And then over here, it's maybe just theta. Some kind of indication, theta Angel greater than theta Brittany. Now, I'm not going to use the angle to solve because I'm going to try and do that work energy theorem. Does energy care about the angle of the ramp? No. So even though it's true, I'm still going to try and use work energy. Angel has more mass than Brittany. Maybe that's important later on. And then no friction, no air resistance. All right. To solve for the speed at the bottom, I'm actually going to start with that no friction, no air resistance. Y'all remember our 3 versions of the work energy theorem, yes? Last time we used the non-conservative a whole bunch, yes? And so this is where I'm going to start. So if there's no friction, no air resistance, you've got 2 people on ramps, basically. Do we have any non-conservative forces? Forces, the answer would be yes. What's the non-conservative force acting on them? Normal force. Isn't there a normal force as they go down the ramp? Is it doing any work? No. So the force is there, but it just doesn't do any work because it's perpendicular to the motion, yes? And so that's true for Brittany on the other side as well. And so no non-conservative work. And so each of these, delta KE and change in potential energy, don't they each have a final minus initial? And last time I showed you if you move the initials to the other side, it kind of takes this conservation of energy approach. And so I'm going to start it, KE initial plus gravitational initial equals KE final plus gravitation final. Now maybe after, 5, 6 problems of writing it out and you kind of get this, oh, I'm getting the same thing I did last time. Maybe if you recognize no non-conservative work, you can start here, okay? So you can start here. Well, in the beginning, we said there is no kinetic. You do have potential. What can I plug in for initial potential energy? MGH. And it's the initial height. Final kinetic energy. What can we plug in for final kinetic energy? 1/2 mv final squared. And then what's true about the final potential energy? It's 0. So if you go all the way to the bottom of the hill, they may not say it, but y'all, in most cases, that lowest point is considered a height of 0. And so I'm going to 0 that out. And so this is the working equation, and we're going to use it to solve for that final speed. And so what do you notice? Why is it going to be the same? Right. And so mass cancels out. You can. I mean, we know something about the mass, right? But it does cancel out. And this is one equation for both. It's not like Angel's going to get a different equation than Brittany. It's one equation that will apply to both people. And so now if we solve it for final, It would be the square root of 2 times g hi. And so gravity is the same. Initial height is same. And so final velocity or speed for each would be the same. Okay, and so answer choice number 3. Everybody okay? Now, if that's feeling weird, you're like, but they have different distances. One's steeper, one's shallower, right? Well, you're kind of getting into part B. Just because they might end at the same speed, does that mean they get there at the same time? Not automatically, okay? And so let's take a look at B, is the time it takes to get to the bottom. We'll say the timer begins at 0 at the top. Is it greater for Angel, greater for Brittany, or the same for both? Now there's 2 ways to do this one. Both of them are kinematics, okay? Now I know that previously I've said, embrace work energy, don't use kinematics. We actually have to here, because some of you might have said, oh, time, I need power. Did they give you anything about power? No, there's no information about power. And it's an object going down a ramp, you can do kinematics, okay? If you look at it similar to a ramp. And so 2 ways with kinematics. We know something about the speeds. We know something about the time that we're looking for. What can we say or determine about acceleration? It's not going to be the same for each. As they go down the ramp, who's going to have a bigger acceleration? Angel. So that steepness, okay, steeper is going to mean greater angle, mg sine theta, greater the angle, we're going to have a greater acceleration, okay? So I'm going to use that. So Angel has a greater acceleration. And so solve it for time. So it would be VF minus VI divided by the acceleration. Well, VF and VI, now we know are the same, right? They both start at rest. VF, we just said they end at the same speed. And so then the acceleration and time have what kind of relationship? Inverse relationship. Remember, AP loves relationships. And so who gets the most time? Who has the smallest denominator for acceleration? Brittany. And so Brittany would take more time. She will lose the race, if you will. Angel will get down quicker. The other kinematics way, someone said, well, can't we just do V equals D over T? And I reminded them that actually that's an average velocity. So it's not just about the final. It's not just about the initial. Hopefully you remember that with constant acceleration, you can do a mathematical average. And so if they both start from rest and they both end at the same speed, then this whole left side will be the same for both people. So in this equation, be careful, D and T have what kind of relationship? Inverse or direct? Nope, they're on the same side. It would be direct because if the numerator increases, if you want to equal the same number, your denominator has to increase the same amount, proportion, right? And so D and T have a direct relationship with this equation. And so who's going to get more time? Well, who has a greater distance traveled? And for that, you kind of got to think back to geometry. We know they're going to have the same height. Brittany has a smaller angle. And if we think about the hypotenuse there, and so this distance for Brittany is going to be bigger than it is for Angel. So it's going to take her more time. Okay. By the way, AP will ask these type of questions. It'll sound like it's multiple choice, but you may not get answers for the multiple choice. Your points lie in your explanation, okay? And so really, I should probably be concluding with, put it in a final summarizing sentence since it says explain. But always have a foundational physics equation, okay? Don't ever like, well, my gut says, you don't get points for your gut, right? All right, next two is about work. So C says, what about the work done by gravity? How are we going to figure out the work done by gravity? Again, there's two approaches we could take to get the same answer. What do y'all think? Work done by gravity. How might we find that? FG parallel to, I got to multiply by a distance. Okay. Now here we got to be careful. The generic equation is distance. But remember, for work to be done, that down force, if I consider straight down, I need to use a straight down height. Or if I use a parallel, FG parallel, I got to use the parallel distance, okay? Well, we know something about the angle, but I'm just going to use the straight up and down ones, okay? To me, that's easier here. And so if I use the straight up and down, it really is FG times H. How do we find FG? Mass times gravity. Hey, that looks familiar. What is that? That's potential energy, right? Now, I didn't show an appreciation for signs, but FYI, the other way is to recognize, well, gravity is conservative, and that leads to negative changes in potential, right? And so you would end up getting that MGH again. Now the negative, there's going to be a downward, a height change in the negative direction, right? So a negative displacement. And so either way you look at it, who has more work done by gravity? They have the same height. Gravity's the same. Is mass? Who has greater mass? Angel is your answer there. Okay. And so again, I talked about summarizing with a sentence. So Angel's greater mass. And you can have supporting work. So you're just kind of doing a summarizing sentence if it says explain. So Angel's greater mass leads to the greater either change in potential energy and or the work done by gravity. Okay. All right. D talks about the normal force. I already alluded to normal force and the work done by normal force. What did we say? It's 0 because normal force is perpendicular to the distance traveled for each, right? So normal force does no work. No work since Fn and distance down the ramp are perpendicular. Now 0 wasn't an answer choice, so what are we going to circle there? It's the same. And then part E, who has a greater kinetic energy at the bottom? They might have the same speed, but kinetic energy is, what's our equation? 1/2 mass times velocity squared. So they have the same speed, but whoever has a greater mass has a greater kinetic energy. So the final answer is Angel. Good deal? Notice in all these, you gotta base your answer on some principle of physics, some reason. It's either a law, it's usually an equation. And see how, if this change happens, how does that affect what you're looking for? Questions on this page? Questions? All right, next page, 10. One more tippers, and then we'll go do some calculating, solving. We'll do a little of each today. So a couple of years ago, my Facebook AP Physics group, somebody brought up about LOL charts. I'm like, what's an LOL chart? I've been teaching physics a long time, watched a lot of videos, looked at a lot of books. I've never seen this LOL chart. Somebody just got cute, y'all. It's bar chart, okay? Here's your L, and then apparently they made this a circle, and then here's your other L. I don't know. So I'm sorry, I'm not cutesy. It's a bar chart, that's all it is. So here we go. And by the way, bar charts may not appear, probably won't appear. If it does, it'll probably be in multiple choice, but I've never seen a free response where students have to fill in a bar chart. Most charts, graphs that physics has you draw is what? Our line graphs, our best fit lines, right? Okay, so draw the straight lines, draw the curved lines. We saw that in the simulation last time. And so here, the bar chart is very common, textbooks, videos, here's another tipper page with it. And so it's just accounting. It's to make sure you don't lose any joules. That's all it is. So actually, they offered paper as well. And so for the last 2 years, it has been modified with the electronic submission portion. And so those that did electronic last June, which by the way, electronic is not on the table for this year. Expect paper, expect normal, expect, okay. But last year in June, it was a lot of multiple choice, okay? And then there were 2 free responses, and the 2 free responses were the ones that were writing heavy, okay? Or typing heavy, I guess. It wasn't just solve. Yeah. You're going to be writing words. You'll be drawing graphs, diagrams. You expect any of it. And actually last year, the paper version, and you can look it up on the College Board, that one's published. We don't have the published electronic versions. They had many versions, is the truth. But the one paper version that's released on their website, every single free response had a graph. You either had to read it, but a lot of them you had to draw it, okay? And so, yeah, be ready with graphs. Well, y'all aren't going to have to worry about it. It's not digital this year. It's not even going to be an option. But yes, they had to submit work. Oh, that was 2 years ago. Last year, it was everything type out or select. So yeah, they didn't do handwritten work submission after that first year. First year COVID, they did, but I guess it was more of a headache than worth it. So last year, for those that did electronic, it had to be typed out or it was multiple choice select. And then you couldn't go back. So once you made a selection, boom, done. That would have made me like, oh, so. But this year, all paper, you're in the gym for 3+ hours, paper and pencil, yes. Are you sure? Okay. Yeah, as everything I've seen, everything's kind of back to normal for the May 2020. Knock on wood, everything, okay. So bar charts, it's very common in energy. It's a way to account for all the energy. And so here we have 100 Newton box. What did they just give us? The weight, also known as the gravitational force. How do you know it's not the mass? It says newtons. Y'all be in the habit of looking at units. Sometimes you're given the mass, sometimes you're given the weight. Here we're given the weight. By the way, can you figure out the mass? Divide by gravity. Divide by 10. Our mass on this problem is 10 kilograms. It's initially 0.4 meters above the surface of the table. Yes. So the formula chart does say 9.8, but a lot of the problems you can use 10. And to confirm this, you can go look at past scoring guidelines. And when there's numerical responses, it always says, well, here's the answer you get with 9.8, parentheses, or this. And that's if you use 10. So I promise you can use 10. And moral of the story, there's not going to be a lot of numerical solve, so maybe it just stays G. Variables is just G, or how it's manipulated, right? But you may not need to do 9.8 or 10, but you can use 10. 10. I mean, I use 10 all the time. The only things that are like set in stone, if you're doing the textbook practice, that's already pre-programmed to be 9.8. But like Canvas, hopefully you've noticed, we program Canvas for 10. Okay, it's a time test. So the quicker you can go on the math, you can focus on the physics.
So if you taking them like mainly concept questions, or is it
so it's concepts, and you'll still do algebra and solving, but you just may not have numbers. So it's like those variable type problems, okay? Yeah, so that was the one we did previous was concept. Here, these are going to be nice numbers. You're not going to need a calculator. AP will do that as well. But the other type is do the algebra with variables, variable solve. And we have one in the future. Okay. All right. So it's moving upward with a kinetic energy of 80 joules. So when, I'm going to use the picture, when it's at this present tense spot, so I'm going to call this my initial location, it is 0.4 meters above the table below or wherever. So we can assume, plus they'll tell us here in a minute, put the 0 point for gravitational energy at the surface of the table. And at this spot, they're telling us not the speed, but they're telling us we have 80 joules, not to be confused with that 80 Newton. That's something different given. But currently, we have 80 joules of kinetic energy. And you can see in the bar chart, that's already colored in, okay? Then a man is applying a constant upward force of 80 newtons with his hand, which by the way is just like a surface, right? So some of you have been asking or maybe thinking, when does normal force do work? Well, this hand is a surface. Whether you call it an applied force or a normal force, is it doing work? If this is a applied force and they say it's moving upwards, is that applied force doing work? Yeah, what kind? Positive, okay? So it is doing a positive work applied. It says complete the energy bar chart for the Earth box system. So a couple days ago, we got nitty-gritty on how systems are defined. This is the norm. It's normal to include the Earth, okay? Before and after, the box is moved upwards a distance of 1 meter. Put the 0 at the table. I say, let's go through the chart. First of all, I want to break down the LOL. The first left side, initial system energy. You can also look at this as the initial mechanical energy. Kinetic plus potential plus potential. Actually, by the way, let's answer this spring question. The third column says PE spring. Did you hear a spring, see a spring? Is there a spring to worry about? No, so we can just 0 joule it, right? And at the end, there's not going to be a spring. And so it's just, nah. And so here we have a mechanical energy to start. Work, it could be positive, it could be negative. So it's that plus or minus. Non-conservative, they use the term external to the system, alluding to the same thing. And then whatever's left over equals your final mechanical energy. Rearrange this. Isn't this non-conservative work equals a change in mechanical? It's our theorem. Rearrange it, it's conservation. All right. What about that second column, PE gravitation? Initial, at the initial location, do we have gravitational potential energy? Yeah, and so I'm just going to show some work here. MGH. MG, we said they already gave us, that's the weight, so don't multiply by 10. It's already 100. Initial height, 0.4. And so what do we get? 40. Now, does that mean we go up 4 tick marks, 4 lines? Well, if you notice, 80 joules was 4 lines. And so each one's 20. Maybe I come here. And so initial mechanical energy is 120 joules. Now, what about the external work? Non-conservative. Well, that applied force or normal force is non-conservative. We said it's doing positive work. Well, how much work is it doing? Well, I hate this, but oh, it's so user-friendly. It only moves up a distance of 1 meter. And so our force applied 80 newtons times 1 meter is also going to give us 80 joules now. And so we'll have 80 joules. And so I can come in 4 lines. There's the O. And it is positive. Tomorrow, maybe there's friction and you go below. So the work applied would be the force applied times the distance, 80 newtons, and they told us in the problem 1 meter. Okay. And then what's left? Well, first of all, final mechanical energy has to equal 200, yes? Now, does it split 100, 100? I don't know. Let's see. Kinetic energy, did they tell us anything about kinetic energy at the end of that 1 meter? No. Can we figure out gravitational potential energy at the end of that 1 meter? Yeah, it's another height. And so final potential energy, MGHF, is that 100 times 1.4 meters. And so that's going to be 140 joules. So go up 7 lines. So 140 joules. So even though we don't know the final speed or the final kinetic energy, if you know the missing link here should equal 200, what is it? 60. 3 lines up. Good deal. No new equation, same equation. We could have done this without the bar chart, right? It's just a visual. It's accounting. Good deal? Okay. Well, let's move on to page 13. Now, some of you on paper, I think the copier, or it's me. Remember I had some copy issues with it. I was fighting the copier when I made these. It may be your page 14. I think that paper might have got flipped. But find this page where we're going to drop a block onto a spring. 13, 14, somewhere in that region. Now, later, I'll show you a simulation where you can actually put the block on the bottom of a spring and have it bounce up and down, up and down, up and down, up and down, okay? And so it can do this, but today we're going to attach the spring to the floor, and it's going to be strong enough to stand on its own. And we're going to take a block on top and drop it, okay? And we're not going to say it bounces off the spring. It's going to land on the spring and then eventually compress it to a max compression, okay? There is not a simulation for this problem, so we're going to draw like comic strip. We're going to draw a progression, okay? Y'all know I like pictures as a visual to see what's going on. And so a 2 kilogram block is dropped. First of all, that's code for what? Well, yes, but initial velocity 0. And it's from a height, capital H, of 5. And if we look in the picture, capital H is identified. Onto a spring that has a constant, and again, it's a springy factor, force factor. It's constant for this problem. 3,000 newtons per meter. That's a really strong spring, just FYI, okay? And so, A, what is the maximum compression of the spring? Now, I'm not going to go straight for it. I'm going to draw like 3 more pictures, and the last one will be the maximum compression. So let's take a look at a couple other places before it reaches maximum compression. So we're going to slow-mo this. And so the next picture I want to draw is the split second it lands on the spring, but no compression. Okay? No compression, but it's fallen that distance h, okay? And then the next one, just kind of do a moderate compression, moderate, okay? And so the next one may be right here. And I'm going to identify this as a special spot here coming up. So kind of give it reference to the whole picture. And then the fourth picture is a maximum compression. So that's a tightly coiled object. I'm going to give it a reference. Now we could draw pictures, after max compression, where the block may go back up. Maybe it launches from the spring. Maybe somehow there's super glue on the spring and it sticks and it just goes up and down, up and down, up and down. Moral of the story, this question doesn't care after. It's just from the fault drop to the max compression. So before we get into solving, let's take a look at the energies. Let's go back to the very first one. We said it's initially going to start at rest. So what energy do we have? Well, kinetic energy would be, what would kinetic energy be? 0 or maximum? It'll be 0. If you have no velocity or speed there, you're not going to have any kinetic energy. Does that mean I don't have any? Well, consider the other 2 types. And spring is here. Gravitation's here. We'll include everybody in our system. We'll do the norm. And so, does it have gravitational potential energy? mgh? Yes. And so it's going to have ug. What about us? There is a spring, but here's what you have to ask yourself. Is the spring being compressed or stretched? Not right now. And so us would equal 0. And so in the spirit of 0 and maximum, if I don't have kinetic, if I don't have elastic, Then all my energy is with gravitational. I'm going to call it a maximum. Plus, it's at a maximum height. It's not going to be any higher in our problem here. And so that's going to be the maximum potential energy, gravitation. Yes? All right. What about second picture? It falls H and just touches the spring, but no compression. Do I have elastic potential energy? No, you have to be compressed. We're just touching barely, tangent touch. What about gravitational potential energy? Do I have it? Yes, but it's not a maximum, so kind of, I've got some. What about kinetic? Yeah, it's not going to be a maximum, right? But I have some. It's not zero. Because it's been in free fall, it speeds up, right? Over a distance of 5 meters. Well, then we get to this middle-ish part. Okay? Let's see if y'all can figure out why I drew it in the middle. That's going to be our equilibrium location. Okay? Now, it may not be dead center, but there is going to be a middle-ish type of location. True story, once it starts springing back up, it could stretch beyond where it had, but in between max compression and max stretch, you would get your equilibrium, okay? But if we call this the equilibrium, well, what kind of energy does it have? We'll go through the process. Is it moving? Yes, so we'll have some kinetic energy. Does it have height? And honestly, I don't know if I've addressed it. To have gravitational potential energy, you need to identify your 0 point. What's a good 0 point? You could do the ground. Well, not even equilibrium. You want your lowest point. Okay, at max compression, we can say that that lowest point that my block will go is going to be the 0 meter mark. So when you're at equilibrium, you still have a distance above. And so we still have gravitational potential energy. What about elastic? Is the spring stretched or compressed? Yeah, some. It's not a maximum, but we have some. Now I am going to write the word maximum by the kinetic, and not because the others equal 0. So I'm not saying it's equal to the maximum constant mechanical energy. This is the point where it's going to go the fastest. Because what's going to be true, force diagram, at equilibrium? Well, gravity is going to be, I'll draw it here on the side. We've got Fg down. And as you pass through equilibrium, that's the nice no acceleration, no net force. And so what force has to balance this weight?
I was going to ask why the equilibrium isn't at when the spring's at rest.
So when you have at rest, yes. So if it's just the spring alone, it's past equilibrium. But when you start putting objects on the spring, it basically has a new equilibrium. And so what I've identified in purple is the equilibrium of my system once it's attached. Good question. And so what force is going to balance that gravitational force to give us that no net force? Elastic, or you can call it spring force, Fs. These are going to be equal and opposite Newton's first law, the balance, right? And so that's what's unique about the equilibrium location. You have no net force, no acceleration. Yes, it's moving, And this is actually where we see V max. If you think about the pendulum, at equilibrium is where you had maximum kinetic, right? I know this isn't a pendulum, but it's same principle. And then we go to max compression. Max compression, we're at the lowest point. So we're at 0 meters. And so gravitational potential will be 0. This is the point where we're going to come to a split-second stop before we change direction. So kinetic energy will equal 0. And you have a maximum compression. So we're going to have a literal maximum potential spring. And it'll equal your mechanical. Does everybody get the breakdown of the energy there? And then at any other points in between, it's going to have levels at somewhere in between. These are just kind of special locations. Okay, so let's answer the first question or get the problem started. What is the maximum compression? And so we know it has maximum potential energy, elastic. Where does it come from? Take that conservation approach. It was converted from, where did it all begin? It came from the gravitational. And so if we look at the very beginning, maybe I call this 1 and this one 4, I can say that the mechanical energy at location 1 is all going to be converted to the mechanical energy at 4. We'll neglect air resistance and any frictional losses, because if we had to take them into account, something would be told to us, okay? And so up in part 1, we said we had a maximum gravitational potential energy. And in the fourth picture, we have a maximum elastic. Okay, so I'm taking a conservation approach. You can still get here by doing the non-conservative work equals a change in kinetic, starts from rest, comes to a stop, 0, change in potential energy, and then a change in elastic potential energy. Okay, and you'll end up with this same thing. Okay, and so equation, gravitational potential energy, mgh, and actually, let me scroll back up to the picture. Is it just h? What's the height change to the lowest point? It's more than 5, yes? It's more than 5, so it's 5 plus something. And isn't that something going to be the same compression distance? Why I called it delta x. And so I'm going to go on and say it's h plus delta x equals the elastic energy all the way at the end. So 1/2 little k delta x squared. Now don't think too quick. Don't start thinking, oh, there's delta x on the left, delta x squared, so I'm going to simplify and get rid of one set. It's actually incorrect. If you distribute mg to both, now you can see that it doesn't cancel out. Okay, nothing cancels out actually, not mass, not displacement. And so now we should have enough numbers to plug in. Mass, they said, is 2. Gravity we'll call 10. The actual height above the spring, they said, was 5. And then 2 times 10 again. There's the compression we're looking for. Equals 1/2. The spring constant, force constant, they said was 3,000. Again, that's super strong. Simplify our numbers. 20 times 5 plus 20 delta x, 1/2 of 3,000. What algebra do we need to do next to solve for delta x? It's been a while. Quadratic. Okay. Now, we did it more so with projectiles, and I said, oh, there's a workaround, okay? Because AP is not going to have you memorize or do the quadratic equation mathematically, okay? You might have to set it up with variables, but mathematically, you won't have to solve for it. They don't give you that equation, right? Yes, there's a song. Yes, there, you know the equation, or maybe the calculator functions you know how to do. So don't stress on this, but I have a calculator program already preset to give it to us. You have to solve for 0 if you remember. And so I'm going to actually subtract the 1500. And then I'll bring in everybody else. You have to identify your A, B, C. Who's A? The negative 1500, B, and then C. And so you put it in the calculator. I'll go in and give it to you. Due to time, you can sing your song. It should come out for a compression distance of 0.265 meters, 26-ish centimeters, okay? By the way, on our exams, we probably won't have you solve with quadratic. Maybe we give you the compression distance and you have to solve for the height, which is only in one place, right? You could do that. So we'll give you a different unknown. Questions on the setup? All right. So that's the maximum compression. And so it falls 5 meters and then it's going to compress the spring 0.26. So that's pretty small compared to the 5, yes? 2, B, whatever. What is the magnitude? What's the value of the maximum acceleration of the block? Now, we didn't really put this on our picture, but what point are we going to get maximum acceleration? We said at equilibrium, it's 0 because there was no net force. Where are you going to get the biggest difference in the force? Where are you going to get the maximum acceleration? Not the second one. No. Fourth. Oh, I didn't hear fourth. Okay, so on the fourth one, let's draw a little diagram. Gravity is going to be the same, right? That doesn't change. But now we're at the lowest point. Well, that spring has just slowed our object down to a stop. It doesn't quit pushing. What direction is it pushing on the block? Up. How much? It's a maximum, and it's going to be bigger than that FG. Okay? And so, yeah, our force is going to be a maximum here. And turns out, how do I connect horizontal springs, pendulums, vertical springs? It's at your extremes. It's max stretch, max compression. It's the left side, it's the right side, okay, of your pendulum. And so here we'll get maximum acceleration. And so let's write a FNet statement. Somewhat old, but we'll incorporate some new. Let's write a FNet statement for B. And so note to self, this happens at max compression. And FNet would be that really big F spring force minus FG. Newton's second law, FNet equals MA. Here's the new spring force. What equation can we plug in for spring force? Y'all remember Hooke's law? That's energy, just K delta X, okay? I'm leaving off the negative. Remember, the negative is technically there, but AP says absolute value. It's there for a concept, not for the math. And so K delta X, and then minus FG equals MG. Mass does not cancel. It's not in every term. And so we'll plug in and solve for acceleration. 2A equals 3,000 times that small compression that we just found, minus 2 times 10. And again, just to save a little bit of time, I got 388 meters per second squared. Goodness gracious, that's a huge acceleration. Yeah, probably this is not realistic, I'll be honest. That's 38 Gs. That's more than the rockets do, right? Probably not realistic. It's okay, we move on. Good? All right, 2 more questions here. C, what if the block had been 4 times as massive? What would the maximum compression have been? And so how does mass relate to that maximum compression? Well, let's think back to part A. And so from part A, we said MGH equaled 1/2 K delta X squared. Now, I'm not going to resolve. Let's just look at it from energy point of view. If you have 4 times the mass, aren't you going to have 4 times the gravitational potential energy to start with? And if energy is conserved, isn't that going to equal 4 times the elastic potential energy you end with? Now, that's not our answer. They want compression. So if I have 4 times the potential energy elastic, what kind of relationship does US have with delta X? It's going to be proportional, directly proportional to the square. And so if this is going to be increased by 4, then my compression will be increased by 2, because 2 squared equals 4. So final answer, your max compression will increase or double, or you could say it would increase by 2. And then back to the original block. So back to the original 2-kilogram block. What if the spring had only compressed 20 centimeters or 0.2 meters? Remember, we compressed 0.26. How much energy would have been dissipated? Okay, I think this is the first time it's coming up. This dissipated word, let's do vocab. What does it mean to dissipate? To emit, to go away from the system, okay? In other words, it gets used by non-conservative forces like friction and drag, and it's never coming back. So it gets used up. And so this is non-conservative work now. It's not going to equal 0. And so here, let's take that change in kinetic plus change in both potentials. And I'm not going to move the initials to the other side, but let's think about each of their final and initial. And so kinetic energy, if we think about the max compression from where it starts from rest and it comes to a split-second stop. And so kinetic energy still has 0 change. Final minus initial of gravitational potential energy, we started with a lot. We ended with none. And so I'll keep that UGI. Elastic potential energy, final minus initial. And so we started with no compression, so initial zeroes out. And we end with max compression. It's different now, but we end with it. And so I'm going to keep and just move it to the left. Hopefully I don't mess you up there. I don't like to start my algebra with negatives. Ugh. Same thing, right? And so this non-conservative work is going to equal this change. And so elastic 1/2 K new delta X squared minus that good old mg H plus that new compression, right? Can't forget that the total height difference is H plus. Don't worry, no quadratic. They gave us the compression. We're solving for non-conservative work. So 1/2 of 3,000. New compression, make sure you're in meters so that we come out in joules, minus 2 times gravity, same height, and then new compression. And just like our other friction and drag questions, it's taking energy away from the system. So it should come out negative. Okay, let me know what you get when you get it. I don't remember this number. 40 what? 44. Okay, that sounds familiar. And again, as long as you were in meters, it should come out in joules. Good deal? Okay, before we leave, I want y'all to try one more thing. It's quick. Go back to page 7, tippers. Do your own ranking, okay? Read it carefully. They give you some hints. And then rank who's going to hit the ground, which arrow is going to hit the ground with the greatest speed. Rank it greatest to least.